All right. Hello and welcome to STEM Online Academy. For those of you who don't know me, I'm Jason Masterakos. The channel is about advanced math and physics concepts, problem-solving questions, and anything else that has to do with these topics. Okay. So a little bit about me. For those of you who don't know, I am a math and physics expert. I guess you can say a mathematician slash physicist. Also, I went to Carleton University for the subjects. I'm also a writer of the book Advanced Integration Techniques, where we explore advanced integrals, applications, and open-ended problems. Okay, so that's a little bit about me. Another thing too, for those of you who don't know my approach to teaching complicated mathematics in general, and advanced science, is I use a three-pillar approach. Okay. Now, why a three-pillar approach? Because quite often problems are much more intricated and complicated than what you may think. Okay. All right. So step one, as I like to always say, I always make sure you understand the problem very well, right? What I mean is the equation, the word problem, whatever it is, make sure you understand it. Step two, model the problem from what you understand, right? Transpose what you understood from the problem and then turn it into a mathematical model that makes sense, okay? And then from that model, it will help you, it will guide you into what makes sense when you do the numerical calculations, okay? Or anything else. It can even help with proofs, mainly for numerical calculations, because if it's an applied problem, you can see where the problem is going from the geometric model, okay? So that is how I go about things. Okay, so let's get right to it. We're going to be looking at, if you see my regular videos, not the live videos, they're all about problems, right? Conceptual problems, either for gifted students, undergraduate to graduate level students, pretty much in the vicinity of trying to help students either conceptually understand the topics or get them actually interested in mathematics. You can be someone who's not really that keen on it, but you've always wanted to learn math, then this is the channel. Okay. So since it's a live channel, I want anyone who's here or is going to be here, I don't know if you're here or not. Sometimes people watch and they just don't say anything. They're shy or something. Don't be shy. Type your questions in the chat if you have any questions. Could be on anything. Well, preferably, let's keep it on the topics at hand that I'm discussing. Okay. So yes, we're going to get started. We're going to go back to my book. For those of you who already know, I'm continuing problems from my book, Advanced Integration Techniques. So let's look at that. Okay. Now, I did just make a video about the last problem. Interesting problem from my book, a multidimensional integral. Okay. And I ran through it. I discussed it. But here, it's interesting because we can have a back and forth dialogue, right? Or a back and forth chat in this case, because you'll just be writing, obviously. So yeah, ask me any questions on the problem, all right? And I think we will get to it then, okay? Just give me a moment. I just want to get my stuff organized. Okay. Yes, I have to share screen, so just one sec. Okay, entire screen. All right, I want to share that. Just give me a moment. All right. Okay, so what we're going to look at is the multidimensional integral. Okay, so if you can look here, this is the cover of my book. It's a multidimensional integral. Okay, I already discussed this in another in an actual video, but that's not a live chat. Here we can go back and forth. Okay, so this one's going to be preferably useful to people who didn't see the other video and are seeing this right now and want hints on how to do a specific problem. I won't here. We can take as much time as needed for you to conceptually understand what's going on, any added questions you want or anything, right? Okay, so we are going to look at this weird integral here. Okay, so the integral of e to the negative x transpose d inverse x dn x equals pi to the n of the determinant d 1/2. So that's what we want to prove. Okay, this is from a theorem that states that it's from a book, and this is a factual theorem. So let D be a symmetric positive definite matrix, and let F map Rm onto R, where f of x is equal to e to the negative x transpose times d inverse of x, and we have this integral here. Okay, that we want to prove. Now, before getting right into it, I am going to show you how this three-pillar technique works that I plan to do for any one of my problems. Okay. All right. By the way, it will help if you have a foundation in integral calculus and linear algebra. Okay. And some measure theory. Well, no, not for this problem. You don't need measure theory for this. But for the book, though, it might be handy if you have some measure theory. But it's not required even for the entire book. So let's look at this. So we're going to take the statement, right? Because this whole thing is a statement. So remember, step one for my problem-solving approach is to define a statement, okay? You have to define what your statement is, otherwise you can't understand what you're doing. So here we have all words that we're dealing with, okay? So what I would do is this: let P be all of this that I highlighted, okay? Statement P would be this, okay? That is statement P. Okay, so this here is all statement P. And then the implication of what this implication gives us is some integral, okay? So the reason why I'm mentioning this is because everything in mathematics, okay, has a foundation in logic, okay? Even though it doesn't say specifically we're using a logical implication, it is in reality every time we have to prove something. So statement P is at the top, okay? P implies Q. That's what this is, okay? It's good to know that just to see. So that's why you see how things relate, and you can pull from tools that you already know from your education, right? So knowing that, you can extrapolate things on P implies Q. All right. Now, this will be handy for the proof, but I also want to show you a model of this as well, if you understand what I mean, okay? So let's go to the web. I already have it set up, okay? So right here, what we have is a simulation. It's a static simulation that I've created with the AI model, but the main point is to get you to see the mathematics in real time for two reasons. One, it helps you make sense out of your later assumptions mathematically, okay? And two, it makes math come alive instead of just being dry, okay? All right, so as you can see here, of the type of problem that we have, okay, of our integral, or our Gaussian integral, all right? You can see here that we have our matrix, right? Which is A, Q, going to be one X transpose AX, okay? And you can see that we have some sort of family of ellipses or family of circles. I don't want to say ellipses exactly based on the eccentricity of the curves here, right? Because the eccentricity will tell you whether or not it's coming up and it's going to be more or circular or not. That's what eccentricity is. All right, so here, very quickly, you can see that we have a very interesting model, and with certain parameters for the eigenvalue. The eigenvalues are important, okay? Eigenvalue lambda 1, lambda 2, rotation angle, all these are important, right? See, the point is when you have the model up, it will reveal certain information that's hidden in the question, but it helps you put things in perspective, what you might need when solving your equations, okay? So you can see here we have the model, all right? And it's just extrapolating back and forth, okay? And if I vary my lambda, my eigenvalue, either it becomes more narrow, right? As lambda increases, right? You can see that these sections are becoming more narrow. As lambda increases, it expands, right? Actually, yeah, as lambda gets greater than 1, that's what I want to say. As lambda gets, not greater than 1, when lambda gets less than 1, the eccentricity is obviously increasing, okay? When lambda gets greater than 1, eccentricity is decreasing, okay? Same for lambda 2. You can vary lambda 2 as well, right? Different type of eccentricity based on the major and semi-major axes, okay, if you know about ellipses, okay? And the rotation angle as well, right? So you have a rotation angle. That means we can just rotate it. Nothing else is unique, okay? So this hopefully will give you a geometric understanding and make things more alive and more interesting of what's going on, okay? All right, so let's get back here. I want to see if anyone is in the chat. My apologies. I just wanted to go through something important. Let's get back to the, so that's 1 second. Desktop. If anyone is here. Okay, not yet. All right. So if we continue on, anyone in the chat that wants to discuss any of the information at this point that I have up, don't be shy. Let me know if there's anything you want to discuss, any misconceptions, any type of thing here. Anything you think I might be missing? Okay, let's continue. All right. All right, so continuing on, right? You'll notice here that we have, continuing on, we have, let's go back to our statement, the theorem, right? So P, statement P, I've highlighted. Statement Q, I've highlighted in yellow. P is in blue, Q is in yellow. So you can see here, when it comes to this proof, right? We want to start with a direct proof. If P, then Q, okay? We want to get from P, and then after, hopefully, our assumptions from P will lead to an implication Q, if possible, okay? So starting this off, I will give you a hint on how to start this off, and then I want any input from the chat, if possible, okay? So for the proof, we know that since D, I've already defined D in the theorem, is a symmetric positive definite matrix, okay? D has to be real and symmetric, okay? Because already in the statement, it says that it's symmetric. So automatically, we have to go by the statement, right? So D is real and symmetric, okay? The next thing is, if D is real and symmetric, right? Well, what do you think? What would that have to mathematically imply? Like, what matrix identities or theorems should we use from linear algebra for this? Because we're talking about real and symmetric positive definite matrices, if I have that correct. Yes. Okay. All right. Any ideas? Any ideas at all? How can we look at this? Now, for anyone who's already seen my regular video on this, it will sort of be cheating. There's no point because this is just doing the same topic again, but in more detail, and obviously chatting back and forth with you guys. Okay. Let me know if there's anything. Any ideas at all? Okay, so there's no ideas. Okay. I don't know if it's here, or you guys are afraid, or you have no idea how to start for new viewers who haven't seen this concept I'm talking about. Okay, so let me go through it. I know it can be hard, a bit tricky to digest. It's not that bad. It's not that hard, but let's go over here. Okay, so back to the board. I'm just going back and forth from you guys seeing me in the chat to going to the board. That's what we're going to do. All right, so for the proof, right, we know that since D is real and positive and symmetric positive definite, then automatically D inverse transpose, right, has to be equivalent to D transpose inverse. Okay, this is a matrix condition, matrix property from linear algebra, right? D inverse transpose equals D transpose inverse. Okay, but then that's equal to D inverse. Why is it equal to D inverse? Well, because D itself, when I mean D, I'm highlighting this. Let me highlight so you understand what I mean. This D, right? This D, okay? This D inverse, okay, is just equal to D. Okay? D inverse equals D. Okay? Right? Because it's a real symmetric positive definite matrix. Okay? Now, another thing too, well, it doesn't matter what I call it. I will let A equal to D inverse. Okay? It doesn't matter. I could have left it as D inverse. The reason why I made it A, can anyone figure out? Why did I make it matrix A? Why did I make it matrix A? I mean, I could call it anything. It doesn't matter. Well, the reason why, okay, is it's just a matter of notation. We are trying to prove that the integral of e to the negative x transpose a x dx, that's what we're trying to prove. This D inverse is not necessary. Usually when we're proving this theorem, it has an A. I use D inverse. But yes, all right, so I'm just letting A equal D inverse, okay? All right, so A is equal to D inverse, where A is equivalent to the matrix D inverse, okay? Now, not only is it equivalent to the inverse, but it's also a invertible matrix, okay? Does that make sense to anybody who's having any problems with that? Any problems? Okay. Right. Make sure to ask me anything, right? Ask me anything. Doesn't have to just be this specifically. Well, since we're in this live show, let's make it relevant. Okay. But in general, you guys can ask me absolutely anything when it comes to problems like this. Okay. Or, problems from my book or math in general, or doesn't matter. The whole verse said this. All right. So when it comes to this, right? So we have where A is an equivalent to the matrix D. What we want to do is we want to try to decompose. Now, I want you guys to sort of relate that. I want you guys to give me some input. What I mean decompose, we know that A equals D inverse. Okay, A equals D inverse. I want to see if anyone in the chat who is watching. Let's go back to the web. Okay, so like this. 1 second. Anyone have any questions on this? Any questions at all? Because we're looking at You have to remember, we're looking at something here that is a positive, definite, real symmetric matrix. Okay. So positive, definite, symmetric matrix. We need to decompose it. We know that A equals D inverse. Okay, so it's cooperating. So let's go. So you guys aren't cooperating at the moment. Either you find it too hard or you're bored. All right, let's go to, let's go to the whiteboard again. Okay, so A equals D inverse. A is equivalent to matrix D. Let's now try to decompose it. What I mean by that is I want to decompose A into some sort of diagonalizable matrix. Excuse me. Okay, it needs to be diagonalizable. Okay, so for those of you who have or are or whatever taken first year linear algebra, all you need to know, well, you need to know a bit more than that, but you need to know the relationship that if I'm diagonalizing matrix A, then A equals P times D P inverse. Okay, you have to relate it to that expression. Okay, so a diagonalizable matrix, right? So in this case, I'm decomposing A into its diagonalizable form. Now, I'm not going to use PD and P inverse. D has been replaced, right? Well, first, P, D, and A in this sense aren't the same as the regular formula, okay? So you need to be careful what you're calling what. You can't use exactly the same variables from the formula here. It won't make any sense given what the statement has already been said, right? So here, A is what we're decomposing. So A has to be on the left-hand side, right? The right-hand side would have to be T lambda T inverse. Let me explain. Okay, I'm going to explain what these new variables are. T is orthonormal. It's orthonormal matrix. Okay, so you should know what orthonormal matrices are. Does anyone know what an orthonormal matrix? That's what I'm going to ask. Okay, let's go back here. Can anyone tell me what an orthonormal matrix is? Excuse me. Sorry about that. That's why I have water here. As in you're talking, your mouth gets dry. Yep. Okay, so does anyone know what a orthonormal matrix is? Oh, come on, guys. Come on. Orthonormal matrices. Okay. Let me just pull up some here, right? Let's go to the web. Okay, I'm just going to get out of here for a second. Okay, so let's go. I just want to show you something interesting. Yep. All right, never mind. Orthonormal matrices, I'll just do it myself. I'll refer. Okay, so orthonormal matrices, right, have to deal with, matrices are orthonormal. So you should have bases vectors, E sub i's, right? Right. If you have E sub I, let me go over here in some extra detail here. You already know what an orthonormal basis is, right? Yes, you have your E sub I and J, and you have your delta. Okay, let me just get eraser. Oh yeah, then do just 1 second. Sorry, 1 sec. All right? So we had our orthonormal matrices there. Okay, just 1 second. I think I erased the board. Oh no. Where was I again? Oh yeah, so we had, let's now try to decompose, right? So we said, let's yeah, I think I erased it by accident. Sorry. Okay, so let me just start writing here. So continuing. Okay, we had T, or should we say we were continuing, we were going to decompose. Okay, so we wanted to, so let me say continuation from the first page. We wanted to decompose everything. Okay, so you want to decompose matrix A. Okay, so we're decomposing. So decompose. I want to use a different color. I'm using blue a lot lately. Where's my stylus? That's what the problem was. Use the eraser on my entire board as opposed to the stylus eraser. Yep. Okay, continuation. So we're looking at this, right? Okay, so I want to use white, not red. Okay, use yellow. Yeah, so let's decompose A. So decompose. Let's decompose matrix A. Right, so matrix, I don't know how it's matrix A. Okay. Now I'm decomposing matrix A. Okay. So again, I'm going to put this right here. So this would mean that A is equal to T lambda T inverse. I want to make my writing better. My apologies. So T lambda T inverse. Okay. Where T is an orthonormal matrix. Okay. So I'll just put over here where T is an orthonormal and orthonormal matrix. Okay, orthonormal matrix, right? So just thinking back to if you had orthonormal bases, right? When we talked about that, we had some little guy Kronecker delta. If you know what that is, E sub I times E sub j is equal to 0 when I can equal j. E sub I times E sub j equals 1 when I equals j. Okay, this type of thing. All right, and where lambda, right, where capital lambda is a diagonal matrix, matrix whose main diagonal is filled with eigenvectors, eigenvalues. Sorry, my mistake. It's filled with eigenvalues. Okay, eigenvalues or lambda. If you've taken linear algebra, you should know this inside and out, right? Eigenvalues of lambda. Okay. All right, so we have that. Now, what we are going to do with this information, I know what my matrix A is. It's a diagonalizable matrix T lambda T inverse. I'm going to substitute in. All right. How should I go about this? Now that I erased, actually, that was good that I erased it because I had some hints, too many hints there. I want to see if you guys, I don't want to do all the work. I want you guys to do something here. Okay. Let's use this. Sorry about that. Good grief. Okay. So please let me know here what you guys are thinking. I need your input. Your input is important. here. Either you guys are very intimidated by the information, or you're finding it not interesting tonight. Let me see if there's anyone there. At the moment. Okay, so going back, right? So how can we do this, right? Just look at the information carefully, right? All right, so let's go over here again. All right, so we have a matrix where the main diagonal is filled with eigenvalue is lambda. Okay. I'm going to substitute. It's obvious. I know what matrix A is, T lambda T inverse. I substitute into my integral. Okay, I want to substitute into my integral. What was that integral again? It's on the first page. E to the negative x transpose the inverse x dnx, okay? So substitute in, okay? I'm going to substitute. Substitute into, okay, I'm just substituting into this guy here, my integral e to the negative x transpose ax dnx. That's what I'm substituting in. Okay, this guy right here. Okay, so what I'm substituting, I'm just putting this in. This will be the integral. Okay, so this is the integral of e to the negative x transpose a. We know what a is, t lambda t inverse. So maybe I'll highlight this in blue. This is my t lambda t inverse. Beside, this is the time to ask questions in real time. Come on, okay? For any of the stuff that you're having difficulty with, right? So t lambda t inverse times x, and then I might go back to just using white here. I just want to highlight the substitution, okay? Just bringing a point home, and that's what I'm substituting. D and x. Okay. So we have this information. Okay. So what can we do? The thing is, we have this now, and it's crucial for you guys to think about. Okay, so the t lambda t inverse is there. But what does this help us, though? Yeah, I substituted it in. That's obviously any time you do math, whatever information, any new things that you deduce, you want to substitute it in, right? But how does that help us? How is that going to further the problem? How's it going to further our approach to this? See if anybody knows. Come on, guys. See if anybody knows how to do this. Looks like nobody knows. So here's a joke. At least the weekends seem to be much more engaging. Here, it feels like I'm just talking to myself. Yes, that's just that's funny. Okay, so no one has any thoughts on how to do this. Okay, so if you go back here, right, get this t inverse, right? I'm going to let there be a substitution. Okay, so I'm going to introduce a new variable y. You'll see y, pun intended. So let y, all right, so let our new variable variable be called y. Okay, be called y. Okay, and y will equal, I'm just going to highlight this as a different color. Okay, this is so you an equation. Y is equal to t transpose. Okay, so t transpose will be y. Okay, t transpose x. There's a reason why I did it. And there's a reason why I called it y, to make it funny. All right, so we have t transpose here. Actually, let me see that. Let me think here. Should be a t, is it tx transpose? tx transpose. Okay, so this would be like a tx transpose. Okay, just give me a moment to correct that. So tx transpose. Okay, and the reason why I'm doing that, I'm being silly. T transpose x. How am I messing that up? T transpose. Yeah, so let's say T transpose x. Okay, and the reason why is because T transpose x, we know that is equal to T inverse x. Why though? Why is this the case? Why is it T inverse x is equal to T transpose x? Because, as we said earlier, our matrix is symmetric. So T inverse is equal to T transpose. Okay. Now I'm going to substitute that information. Okay, I'm going to substitute that new information that we have here. So let's substitute in. Okay, substitute that in. Okay, so substitute. Just one sec. So substitute back into our integral. Okay, substitute back into this guy here. Okay. So integral e to the negative x transpose, x transpose what do we call it? We said t lambda t inverse. Okay, so let's put that again. So t capital lambda t inverse. Okay, times x. Make my lambda better. Sorry about that. T lambda inverse x. Okay, then this is dnx. So we're going to substitute this. Our new integral will be this. Okay, so the integral will be e to the, now it's going to be negative y transpose capital lambda, let's see, it is y, capital M y, d n y. Okay. Anyone in the chat? Anyone in the chat that wants to offer anything new here? Anyone offer anything new? Let me see in the chat. Anyone over there? Let me see. No, nothing I can see right now. Okay, so I'm going to go back. All right, so let's go back over here. So we have this integral now, right? So e negative y transpose lambda y, okay, and then dny. Okay, so then from here, what we're doing is just replacing what we know about our diagonalizable matrix with y's. Okay, I need to call it something, because just having t lambda t inverse is just too messy. I want to replace it with a variable. I want to make some connections. I want to replace it with any new variable such that it's in a mathematical form that I know I can connect to something else, if that makes sense. Something else that I already know mathematically in terms of equations or something. Okay, so now we have this. Now, it still looks messy, it still looks problematic. So what we can do now with this, okay, notice we have negative y transpose lambda y. So y transpose lambda y, okay? I'm going to refer to my other video. So I'm going to skip a little bit. You can refer to my other video for the next step, right? But I don't want to go through the whole thing and make you guys bored. You're already bored as it is. So you can see here now what we're going to get is we're going to get at this integral. Okay, so let me write it out. Okay, so this integral over here. Okay, so e negative x transpose t capital lambda t inverse of x. Okay, so dnx is equal to this, as we said. We know that this is already true. So this can be reduced to integral, actually pi times an integral. Okay, so it turns out this becomes pi from k equals 1 to n of the integral of e, right? E to the negative lambda y. Let's say y. I'll use I here. It doesn't matter what I call my index for the product because we have n dimensional Gaussian products here. That's why I'm doing this. That's why it's a pi product. Integral e to the negative lambda yi squared dyi. Okay. As I said, if you got sort of lost there, you can refer to the other video on the exact steps. Okay. But I have to sort of speed up. All right, so we have this pi product here, and then after the point of this is we have a Gaussian integral. Now notice that I'm going to bring this up pretty quickly. Note that any Gaussian integral, we can go over here. Yes, this is not my other page. So yes, continuing. Good. All right, so from the previous page, we had the integral of e to negative y transpose lambda y dy. Okay, I replaced it with a pi product. Okay, capital pi product because you have n or k amounts of Gaussian products. Okay, so we have e to negative lambda yi squared, right, and then dy subject k. Okay. Any questions on that? Do you guys have any questions on this part here? This part is a bit annoying, annoyingly tricky, just annoying in general. Okay, any of you guys have anything that you want to? No, that's not what I'm looking for. Sorry, that's not. Anyone interested in solving this? Yeah, let's see here. It's not at the moment. Oh, you guys are not interested in this particular problem today. Don't worry, they'll get more interesting as the days go on. All right, so let's continue back. All right, so this integral right here, right? And the reason I'm getting this is because we have a row vector x with x1 to xn, okay? And dnx equals the pi product I equals 1 to n of dxi, all right? Because any nth differential is a pi product, right? With dx subscript I, okay? Now, what I'm going to do in the next step is this is equivalent to pi from k equals 1 to n of square root of pi over lambda k. This square root of pi over lambda k is just what the Gaussian integral is, okay? I'm going to write to the side here, integral of e to the negative ax squared dx is always equivalent to root pi over a. That's why we have this. In this case, a is the little lambda k. Okay, should be little lambda k. Yeah, little lambda k. All right, so now we have this. Now, what ends up happening, so that's the reason why we were able to replace that integral over here, because, just 1 second, this integral right here is a Gaussian integral, right? So root pi over lambda k. So now that I have that, I can pull in my pi operator. And what I mean by that is the pi can go underneath, the capital pi can go underneath the little, under the square root and affect little pi. But a capital pi product of little pi is a pi to the nth power, little pi to the nth power. Why is that? Well, we know that anytime you have this, okay, k equals 1 to n of, let's say, a subscript k, this is a1, a2, a3, so on, all the way up to a sub n. So I'm multiplying a n number of times. Here I'm multiplying pi n number of times. But if I multiply pi n number of times, that's the same as saying little pi to the n. Okay? Hope that answers your question. I want you guys to ask me questions on this, because this stuff is not necessarily that straightforward. Okay? Let me see. Is any problem with this? No, it looks like no. Any problems at all with the pi product? Okay, so let's go back. All right, so we have this guy here, right? So pi from k equals 1 to n, root pi lambda k. And we said this gave us pi to the n all over capital pi lambda k. Okay, the lambda pi of lambda k, capital pi of lambda k. Remember, we're multiplying lambda k number of times, lambda 1, lambda 2, lambda 3, all the way up to lambda k. So what does that look like? And remember, lambda is related to something. Lambda is the main, is the diagonals of the that diagonal matrix, capital lambda, right? On the side here, think about it, right? Capital lambda, okay, is equal to the diagonals of the matrix that had lambda 1 to lambda k, right? See, this is the good thing about live chats. We can not only discuss a video I did before, but we talk back and forth. I put notes onto the side that weren't normally thought of in the regular videos, but it might be handy for both of us, and more handy for you because you'll be able to conceptualize some extra steps that I didn't even think of would be necessary. Okay, so this is the reason why capital lambda is equal diagonal of lambda 1, lambda 2, lambda k. And that's just a determinant, right? That's the determinant of lambda, right? Lambda is a matrix. Taking the main diagonal of the lambda means that it's the main diagonal, upper and lower triangular matrix. Okay, everything else is 0 except for the main diagonal. So we just have root pi to the n all over lambda, determinant of lambda. Okay. Now, since we know that determinant A is equal to determinant of t lambda t inverse, obviously it is, right? Determinant of A is equal to determinant of t lambda t inverse. Okay, because we said t lambda t inverse is already A. So the determinant of A would have to be the determinant of t lambda t inverse. That was from the previous page. There's no further explanation, I think, on that, right? Unless there needs to be. Does anyone agree with that or disagree? Anyone agree or disagree? Okay, so we can go back. All right, so let's go back here. Just give me a moment to extrapolate my ideas here. Having a live show sometimes is intimidating even for the person who's making it. All right, so we have capital lambda, okay, right? Because obviously that determinant can be split up. Determinant of t times determinant of lambda, determinant of t inverse. Okay. TET inverse, same thing as the matrix identity, A times A inverse is the identity, right? TET inverse is identity. Identity matrix times lambda is just lambda. Okay, so A is equal to lambda. So now that we know that, we can substitute back into our original integral, e to the negative x transpose ax dnx, and this is equal to root pi to the n all over determinant of A, because we said initially it was lambda, as you can see here, but we've shown that lambda is equal to A, so I can just put A there. And then finally, what we can do is this. Integral of e to the negative x transpose of ax dnx is equal to root pi to the n of A. Okay, and that is it. We've proven what we needed to prove on page 1. Okay. All right. So that is it. You can see that we have a very interesting type of proof here. I hope this gets you guys invigorated about when it comes to calculus, linear algebra, okay, or any other area of math. Math and stats, doesn't matter what it is, okay. But tonight has been my pleasure to show you how this works. Again, you can ask me absolutely anything. I'm always free to talk. My office hours are anytime. Well, Monday to Friday, I'm free practically from 9 a.m. Eastern to 5 p.m. I don't know what I'm saying. To 6 p.m. Eastern. Okay, so those are my office hours. All right, ask me absolutely anything. Doesn't matter what it is. It can be homework, APIB homework, university homework for undergraduates, graduate level homework, research papers for graduates. Just doesn't matter. I'm very well versed in mathematics. You're going to see that, and more importantly, I want you guys, for those of you who already are in this field, how I can make, but want to be able to conceptually understand the problems better. That's my job. I'm trying to invigorate your mathematical intuition with problems that are not standard. That's what this book is. But I hope that it's going to help, right? So for the book, you can, if you're interested in learning more about mathematical methods, specifically on integrals, you can check out the link in my description. Okay, will be there in the description. And also, if you're looking for, as I said, tutoring expertise, I'm always available. Or you can just put things in the chat, interact with me, even though this is a live show. I mean, maybe after people will see this and be like, okay, no, this is cool, or this is not, or I want a better simulation, or help me with this, help me with that, how this is related. Okay. So I hope tonight was interesting and that you found it very, very interesting. Okay. And don't worry, there'll be plenty of more math, physics, and tech. I also do tech as well. Tech videos on this specific subject. All right. All right. That's it. Have a good night. And stay tuned. They're going to get even better and more interesting. Have a good night, guys. Bye-bye.